Hello and welcome to this presentation of an empirical analysis of container introspection tools and techniques. My name is Bradley Morgan. I'm a PhD student in computer science at Auburn University, and today's discussion will be somewhat of an observational study that attempts to deconstruct a current trend within the IT industry, containers, into its fundamental concepts and components in an effort to evaluate potential security risks. Containers, or lightweight virtualization, are an interesting topic in terms of security. Over the past decade, the demand for rapid software deployment within the enterprise has given rise to practices that rely heavily on the use of containers. In contrast to traditional hypervisor-based virtualization, containers leverage core system functionality from a shared OS kernel, which leads to concerns that kernel vulnerabilities cascade into the containers that they host. Additionally, the ability to quickly and easily deploy containers leads to duplicated or unnecessary services and resource publication, or just simply overexposure of a host system. Another consideration is the reliance of organizations on third-party software such as Docker, Containerd, Kubernetes, etc., to implement the technology. These third-party services introduce additional potential for vulnerability in that organizations are at the mercy of the security consciousness of the entities that develop and distribute this code. So all this considered, a careful and thorough review of the underlying technologies and potential security weaknesses of containers is a worthwhile endeavor. To provide some insight into the driving forces behind the adoption of containers, we can view them as essentially a lighter weight version of traditional virtualization. Uh, Virtual machines, which also provide similar benefits for the isolation of services, employ a hypervisor, which allows for the provisioning of multiple highly isolated independent operating systems on a single host. This high level of isolation, however, introduces significant overhead in that each virtual machine must be provisioned, configured, and maintained separately, which can be very costly in terms of both time and money. Containers reduce this overhead by replacing the hypervisor with the operating system itself and provide the necessary abstraction needed for isolation through the use of namespaces implemented in the kernel itself. Namespaces are a critical concept for understanding the implementation of containers. Namespaces provide the abstraction that is needed to isolate and constrain resources for processes. Here we see at the lowest level there is the host OS and the kernel, and a global namespace is provisioned by the operating system to encapsulate all available system resources from which all other namespaces will be defined. By default, a namespace created here will inherit the global resources, but specific constraints can be defined through providing various parameters, which we'll discuss in a later slide. You can create any number of namespaces within the global namespace and also within a namespace itself. Each subsequently defined namespace will inherit from its parent in a hierarchy so that it functions essentially in its own operating environment, unaware of any systemic context outside of what it has been granted. In the Linux kernel, namespaces are categorized into 7 primary subtypes called namespace types. These provide the granularity needed for defining the core capabilities afforded to a namespace and consequently a container. The first namespace type listed here, cgroups, which is arguably the most significant namespace type, allows the operating system to measure and control the use of resources by a particular process tree. So you can limit the amount of memory, CPU, etc. that a specific namespace will be able to use. Processes often need to pass messages to one another in order to pass data or perform synchronization tasks. The interprocess communication, or IPC namespace type, provides control over what processes the namespace can communicate with by restricting access to the various message queues. For file system isolation, the mount namespace type provides the capability to create namespace-specific mount points on which to store internally accessible data. The network namespace type virtualizes the entire network stack for a given namespace, allowing control and isolation of network devices, routing tables, firewall rules, etc., within the confines of a specified namespace. The process ID or PID namespace type maintains an isolated accounting mechanism for the assignment of namespace internal process identifiers. The Unix timesharing or UTS namespace type deals primarily with control over host and domain names for a namespace. This functionality leverages a system called to uname, which returns the UTS name data structure, and that explains the way it's named there, UTS. And finally, the user ID namespace type allows user and group identities to be created and isolated within a namespace. Notably, for this one, and in contrast to all other namespace types, administrative privilege is not required to instantiate the UID namespace type. To control the use of namespaces and allow them to be specified and provide an interface to their functionality, Linux provides an application program interface consisting of three main functions. These are implemented typically in C code, but you can see the three main functions here are clone for creating a new namespace, set ns for joining an existing namespace, and unshare for leaving a namespace. And we'll delve into these in further detail here in a couple slides. As is typical with Linux operating systems, a file system representation of namespace resources is also provided. This involves the use of a highly privileged and somewhat obfuscated file system called NSFS, namespace file system, which is tightly woven within the Linux kernel. However, some visibility into the process namespace allocation is apparent within the /proc subsystem, where process IDs are mapped to their respective namespaces and corresponding namespace type. You can see here the syntax or the pathing mechanism for that is /proc, the process ID, the /ns for namespace, and then the corresponding type, whether that's PID, UID, cgroup. All those files are created as NSFS file types down in that substructure or path. The clone system call wrapper provides broad capabilities for spawning new processes. This function provides much more capability beyond namespaces or namespace allocation itself, but it essentially becomes part of the namespace API through the use of the flags parameter, and that's where you can specify namespace types in order to create new processes with those provided namespace properties. Set_ns can be used to assign a process to a specific namespace through providing the necessary /proc file descriptor, as we discussed, along with constraints. In the case of NS type, a 0 can be passed to indicate all namespaces. The unshare function operates similarly to the clone function in that it can alter the execution context of a process in terms of the provided namespace parameters. However, unshare performs this action on an existing process without creating a new one. Conveniently, Linux provides command line tools that implement namespace functionality. These are basically implementations using the API functions we discussed. And here you can see you have NSEnter and unshare. NSEnter is roughly correlated to set_ns, and unshare is an implementation of the API function of the same name. Also of significance are the lsns and the systemd-cgls commands. lsns allows you to list the existing namespace contacts that are present on the system. And systemd-cgls allows you to view the C groups that have been defined in the current execution context within a Linux operating system. And so these tools are helpful for interfacing with namespaces, accessing them, and performing various functions on namespaces. In order to perform experimentation with container introspection, one final concept needs to be understood. There's an additional abstraction performed by most implementations of a container runtime environment platform as a service software stacks. These tools, such as Docker or Singularity, provide convenient ways to create and manage container deployment, usually adhering to the Open Container Initiative Standardization, or OCI, for how they define container images and perform their execution. On the left side here, you see the more general categorization of the typical implementation components mapped to the Docker specific items in the middle. For these runtime environments, an API usually exists at the higher levels that interprets and translates actions or commands, which are then passed down the stack to the lower level components. It's important to note that the higher level API daemon, like Docker D, outsources much of its work to the other running services such as Containerd, ultimately cascading down to the aforementioned namespace API and the core kernel functionality. Okay, so now that we have a better understanding of the underlying concepts and technical components involved in containerization, we can begin our experimentation to try to find potential points of weakness in their implementation. The goal here, again, is mostly observational. So using standard tools, system tools, we want to perform an analysis of what is happening within the container runtime when we instantiate a container and find different methods for container process discovery and interaction. In this experimentation, we use the Docker platform as a service software stack to provision a simple web server, observe the system behavior when performing certain API operations, and attempt to interact with the container using more standard, generally available system tools in order to find the potential points of concern in regard to security and privacy. Okay, so here we have a system standard Linux distribution, CentOS, and we're running the Docker stack, and you can see here that the systemd service reports this service file in use for starting, stopping, controlling the Docker daemon. And you can see the exec start command gives us a little bit of a hint. It's spinning up the Docker daemon using a host name descriptor with a file descriptor, and then of importance is the containerd parameter. So we have some indication that containerd is being used with that particular socket file. So let's take a look at our processes, and we'll look to see what Docker process is running. And let's just do an strace on the Docker daemon to see what it looks like when we instantiate a container. So here we're just going to say, we're going to follow the threads, and we're specifically interested in the write calls to the file system to see what it is that the Docker daemon is doing, and we're going to grep for containerd to see if there's anything specific to containerd, since we know that that's in use. So on the right side there, you can see that we have a single image there. It's a web server, HTTPD, and we'll just start that. And when we do, you see on the left side that we've got the output of our write command using a file descriptor 9. And you can see there are a lot of references to containerd. The runc command is of interest there as well. Runc is what's going to actually instantiate the container. So now that we have the file descriptor, let's take a look and see what exactly is being done there in terms of file descriptor 9 in regard to containerd. And when we use this ss command to see what the socket looks like, we can see that 2 ports are open, the 7917 and 7928. So let's just take a look at those. Using the lsof command, list the open files, we can see that that socket file is in use, the containerd socket file, and then we've got a PID there associated with containerd or container. So let's stop the Docker image, and let's do a trace on that process to see what's going on there. So we're going to run the strace similar to what we did last time. I'm going to follow the threads. This time we're interested in the exec ve command to see what's being called, system calls or any calls that are of interest within that running process, and then we'll start up the container again. And here we can see that the strace has returned some of the calls to exec ve. It's calling the containerd-shim. It's calling runc with a lot of different options there. And then we follow that down all the way to the last call that we get, which should be a call to the web server, HTTPD. So there's another call to runc, which is instantiating the container. And then within the container itself, we see that the HTTP foreground command and the Apache 2 HTTP daemon commands are being executed within the container. So now we can get a process tree of that PID that was returned and see what exactly is running from the root of that process. When we follow that along, systemd calls containerd.shim, and then finally into the namespace. change for the HTTPD process. So you can see it's changed the namespace of IPC, mount, etc. So now if we just grep for that process in our normal PS, we'll see that the 8691 process is running, and that's going to be the process that we're interested in looking at. Okay, so by using strace, pstree, and looking at the socket files using SS and the other various standard system tools, we could see that gave us some insight into how Docker instantiates a container through calls to containerd and then subsequent calls to runc, etc. But a shortcut for finding the PIDs of running container processes is just to use the lsns command, which will show us the existing namespaces and associated PIDs on a system. So when we run that here, we get a different process ID from what we saw previously, and that's just because I've run several additional Docker starts and stops. But here we can see the PID of interest is this one, and now we'll use the nsinter command to see if we can access the namespace types of the running container. So first, let's take a look at the UTS namespace, and that's the one, remember, that deals with domain and host names. And here we can see that when we perform an nsinter to enter the host name namespace, or the UTS namespace, that the host name is returned from the perspective of the container. It's different from the actual host. Similarly, using the network namespace types, we can see that it returns different network devices from that of the host. We can also take a look down into the /proc directory to demonstrate how Linux assigns the various pointers to the namespace pseudo files using the NSFS file system. Again, these are sort of a file obfuscation that aren't really available to be manipulated without some serious low-level work. But what we see here is basically pointers to the file inode numbers within the file system, and we see that one exists for each of the namespace types that we discussed. And we can also enter the container interactively by requesting access to all existing namespace types. And we saw the HTTPD container instantiated the mount, UTS, IPC, PID, and net types. But what about user? So when we enter the namespace, we see is inherited the user and group mappings of the parent global namespace, but using unshare capital U, we can shift the internal namespace to a new user and group mapping, which results in a new and empty mapping of the user and group IDs. So here you can see that these inode numbers match, but when we shifted to the new user namespace, that user inode has changed. So now we're in a different execution context in terms of the user and group mappings. So we've now demonstrated how to use of standard general system tools from the host perspective. It can give us some insight into the underlying operational components of containers and how we can use those tools to access and manipulate some of the namespace properties and thus the execution context of a container itself. I think the important thing to note on what was demonstrated here is that the vast majority of the tools that we used, things like strace, pstree, nsinter, unshare, etc., are all tools that work outside of any specific container runtime implementation and at a more systemic level, which provides much more opportunity for performing operations that could potentially result in unexpected or unintended behavior. That said, we've not yet demonstrated any tangible exploits, so more work obviously needs to be done to provide a referential example of how these tools can be used to achieve our primary goal of identifying and exploiting weaknesses. So hopefully by the time the full paper is complete, we'll be able to demonstrate a host to container or container to host privilege escalation exploit. Because the instantiation of the user namespace type can be done without administrative privileges, this looks to me like a good opportunity to pursue. And this will most likely involve some further experimentation with the namespace command line tools and the development of C code that explores the variations in the function call parameters, etc., to find unexpected or unintended results. So I hope you found what was presented here to be enlightening and that it helped further your understanding of the fundamentals and concepts involved in the use of containers. I think, if anything, the findings so far serve as a good foundation on which to build a threat model for the categorization and identification of likely vulnerabilities, and I hope to present more specific security-focused findings in the full paper. For now, this summarizes what has been achieved so far, and if you have any questions or feedback, please feel free to send me an email or get in touch. That concludes this presentation of my observational analysis of container introspection tools and techniques. Thanks for your time.